Hi everyone, welcome back. Just looking at some simple cases on how to calculate a confidence interval when we go out and we have one lot of data. We have one sample proportion. How do we get a sample proportion? We have any situation we want to find out about whether someone likes a politician, whether people want a construction to go ahead nearby, and you go and talk to those people and you find out what they think about it. And you're looking at, they'll either say yes, they like it, or no, they don't like it. So let's have a look at what we've got here. I'm going to talk about pizza. If I go out and I talk to 100 people, and out of 100 people, 70 say they like pizza, just randomly pick people in the local area, or I try to go wider area, try to make it as random as I possibly can, and that's called our p hat. So it's the only estimate we know of the actual true population proportion. So this is not a population proportion, it's one sample proportion. Of course, if I wanted more details, I could just go talk to more people. Let's have a look at what that means. Once you get the p hat, which is basically becomes your average or your mean to the whole situation, to get the standard deviation using that value, we know it's going to be PQ on N. Now, I can go through at length what that is. I've already gone it with my students, so in this case, I'm just looking for the basics of what's going on. Now, in this case, it actually becomes a p hat and it becomes a q hat, which we don't know the real p. We only know an estimate for that p from this one sample that we took out there. So that would be the square root of 0.7. Now a lot of people write q as 1 minus p, which is 1 minus 0.7, which is 0.3. I don't tend to fuss for that. I leave it as that, and that's 100. And I've got my figures, because we took a sample of 100, and I've got my figure over here. That's the standard deviation for that sample proportion that we picked, 0.046. So how do we get a confidence interval? We're looking at a 95% confidence interval. So we're looking at, we want to be correct 95% of the time. So we're looking at these cutoffs here, which make a 95% confidence interval. I always talk about z-scores come to the rescue. So the z-scores for 1.96 are minus 95%, are minus 1.96 and 1.96. A lot of people around, by the way, they're just a z-score for 95%. So a lot of people, though, won't use 1.96 around the world. If you're watching videos, people will use 2. So what we're going to do now is we're going to calculate the margin of error. This part here, from the middle, which is our p hat, out to where those cutoffs are, is called the margin of error. A lot of people refer it as just MOE. So let's look at what we know. We have a p hat. We're going to add a z-score, because we have a z-score here, times by the standard deviation. I'm going to write it for the moment so you get it in your head. That's a p hat by a q hat on N. And that's our upper limit. And then our lower limit's going to be the p hat minus the same z-score by the same standard deviation. So you can see the symmetry in what's going on here. So we had a p hat, which is 0.7. We've got a z-score for a 95% confidence interval of 1.96 times by the standard deviation, which I've already calculated up here to be 0.046. So let's have a look what that is. That's going to be 1.96 times by that part times by that I've already got written down here is about 0.09. So that would give me altogether 0.79, which is the upper limit, the value we're going to use for the top of the confidence interval. Come down to this one here, and I've got the same 0.7 minus the 1.96 times by the same standard deviation, 0.046, which of course, again, I'm going to say one more time, that calculation there is the margin of error. So if these pens work, that's our margin of error. And if you look back to the diagram, it's from the middle of the normal distribution through to where we're cutting off on each end, half of that distance across there. So this one's going to be 0.7 minus the 0.09, which ends up being 0.61. So what we now can say is that that's 61% and that's 79%. Now let's have a look at the words that we talk about. That's our confidence interval. We're talking about our sample proportion, but I now can talk about the true proportion is somewhere we are 95% confident that the sample proportion is somewhere between 61 and 79%. Does that mean we're always going to be correct? 95% means we're going to be wrong 1 out of 20 times. So basically all around the world people see it as acceptable that you're looking at getting it wrong 1 out of 20 times. So how can we increase what we're doing? Do more samples. The other thing you can do, which is much clearer, is simply to increase our sample size. So let's say we start it all over again. So now if we take a sample of 1,000, we're expecting more accuracy, unless we walk into an area where we know like the people in that area prefer pizza in a big way. So you've got to be careful, of course, that's a random sample, or as random as you can get it to be, which is always hard to do. So now, instead of getting a sample of 70 out of 100, let's say, I'm going to make the figures easier, we've got 700 out of 1,000. So we still have a p-hat of 0.7. So how do we calculate our standard deviation using the sample proportion? It's still going to be the PQ on N. So it's still 0.7 by 0.3 on 1,000, and that turns out to be this number over here, 0.10145. Now, we're still looking at the 95% confidence interval. By the way, if we were looking at the 90% confidence interval here in Western Australia, we memorise the numbers, you know in your head, but you can look them up, or you can look them up on your calculator. If it was a 90% confidence interval, we're talking about 1.645 for a Z-score. And we go minus 1.645 for a Z-score. They're the two most common, is a 90% and a 95%. So what are we going to calculate? We're going to start at our p-hat, we're going to add the margin of error, and we're going to subtract the margin of error to get these limits, these endpoints where we cut off for our confidence interval. So most people will be okay now, but let's have a quick look at it. It's p-hat plus the margin of error. I'm just going to write margin of error. So this is p-hat minus the margin of error. So we now know we had 0.7, and we're going to add the margin of error, by the way I am going to say it, which is Z by the standard deviation for our p-hat, 0.7, which is our Z-score, 1.96, times by our standard deviation, which turns out to be 0.028, which turns about 0.728, which is about 73%. Now, most people aren't very fussy about decimals. They're usually wanting whole numbers here, or probably, or maybe one decimal place at most for those figures. So over here we'll have our 0.7, and we go minus our Z-score by our standard deviation for the p-hat. So that's 0.7 minus, most of you are okay now probably get the message. So if I did that in my head, that's 0.672, and that one would be 67%. Now our confidence interval, we're saying the population proportion is somewhere, we expect is somewhere between 67% and 73%, 95% of the time. So that's our 95% confidence interval for working out on a 700 out of 1,000. Thanks for watching. Bye for now.